Night lecture. Assalamualaikum. This is Dr. Night, and this is class ECC 3129 and as well as ECC 3119. The lecture slides is already uploaded on Putra Blast. You can download that if you wish to write on the lecture slide while I'm giving a lecture. Okay, so we are going to do this again, the indirect frequency modulator part. The indirect FM generator. And we will also discuss the quadrature detector concept. And we are going to dive a little bit deeper in phase locked loop FM detector. I know I've talked about it before, but I feel like we weren't really focusing because we were trying to prepare for a test and this was not on the test. I think everyone was like, I don't want to listen to this, so let's just do it again. Okay, so I have a problem to get things, get your brains working again. A phase modulator produces a total phase shift of 45 degrees. Okay, so phase shift is given by this symbol. I believe I'm recording, right? Okay, this is phase shift. This is phase symbol. If it is phase shift. So you have this delta. Because why? Because it is going to be phase 1 minus phase 2 of something, and this is going to be delta phase, delta phi. Okay, so phase shift is a shift. The shift is represented by this delta. So delta means difference, right? Okay, so we have this information, 45 degrees. So what we need to do is when we talk about phase, we are always talking about it in radians. So we have to convert 45 degrees to radians. And then another information that we have is the modulating frequency range is 300 to 4,000. So this is our FM. This is going to be our total. Okay, if after we have converted it to radians, what is the maximum frequency deviation possible? So now I have a little recap for you down here. It's a little bit small. Let's zoom it a bit. A simple formula for determining the amount of frequency deviation FD represented by a specific phase angle is, so here we have FD, which is frequency deviation, F is frequency, and equals to delta phi, which is phase shift, and we have our FM. So here the delta phi is change in phase angle in radians, okay, and FM is modulating signal frequency. So let's go back to the problem. So let's try to use this equation. So FD is delta phi FM. So we should change this 45 degrees first. So how should we change it? I think I have the answer here. So here we have, I've changed FD to total FD, okay, which means that this phase shift also needs to be total as well, okay? If this is just FD, then it becomes delta phi. If this is F, it also becomes delta phi total. Okay, so 45 degrees times with pi radians over 180 degrees will give me something in radians. And then the frequency is 300 to 4,000. What is the maximum frequency deviation possible? So here I am inserting FM as 4,000 because we're talking about the maximum. I can also do the 300 hertz, no problem. So you would also have it like this. But obviously this is not going to be the maximum because the value is small. But you can try if you want to prove it. You would start with 300 and then you get the answer, and then you plug in FM for 4,000 and you would get this answer. So this is just using the equation and understanding what the question wants. So here it's saying produce a total phase shift, which means that this guy is total. Therefore, the FD is also total frequency deviation. And the answer is total. Remember, when we're talking about deviation, what are we talking about is, this is our FC, and then we can have it very fast, and we can have it stretch very slow. So this is the deviation, FC plus FD, FC minus FD. This is what the deviation means. Okay, it's deviating from the carrier frequency, or it's deviating from the center. So this guy is giving us the total, which means that we need to divide this by 2 to get the plus minus FD. Plus minus FD is not total. Total is 2FD. Okay. Was that okay for everyone? I know our brains are a little bit rusty.
Okay.
The mid-term break. Okay. Um,
Tapi soalan tu maksimum kan. So maksimum baik ambil 4,000 kan. Daripada 300.
yes. Yes, correct. Because it's talking about maximum. That is why I inserted FMS 4000.
Kalau tak ada maksimum?
Then you would have to find out both values and find the range.
Oh, okay. Oh, jawapan tinggal dalam pi boleh tak? 1,000 pi. Ke
Apa?
better jawapan tu
Aha.
tinggal dalam 1,000 pi tak apa ke?
Tinggal dalam 1000 pi.
Yang 3.142. So like dia jadi 3,142.
Oh, yes, yes. You can actually bundarkan lah. What do you call bundar? Yeah, you can round it off. Actually, I accept, but typically we would go for 2 decimal places in the test or in the exam. But if in any case your working steps are correct, I just give you marks.
Okay.
All right, moving on. Again, this video is recorded, so you can always revisit this. So the next problem is a varactor phase modulator like the one in the figure, this guy, has a resistance value of 3.3 kilo ohms. So this is what we have.
Okay, I found this on the web, the resistance value of 3.3 kilograms. So this is what we have. Check it out.
Sorry, my Siri is responding. Okay. The capacitance of the varactor at the center unmodulated frequency is 40 picofarad. Okay, so this is our C. Okay. What does it mean by the capacitance? Okay, so we have a dot here. The capacitance of the varactor at the center unmodulated frequency, which means that the capacitance value at FC. Okay, at the center frequency. Okay, let me not write it like that. That looks like a C. Okay, at. That's supposed to be an at, okay? And the carry frequency is 1 megahertz. So if we were to make sense of this, so this would look like something like this. Capacitor on the right. So this is the capacitance value, C, and this would be F. So here it's saying C is 40 picofarad at FC. So, whoops. FC is 1 megahertz. Okay, this is FC, and this is 40 picofarad. This is going to be capacitance, and this is going to be frequency. So if we increase the frequency, therefore the capacitance will decrease. If we decrease the frequency, the capacitance will increase. Okay. Okay, so this is increasing. This guy goes down. And this is decreasing the frequency over here. And this gives us a higher capacitance value. So this is how a VCO works, or a varactor works. You change the frequency or you change the voltage, you get a different capacitance. Excuse me. Okay, so what is the phase angle? So let's move on to this part. What is the phase angle? So we have C. First, let's try to imagine what kind of equation will phase angle be related in this problem. So phase angle for this kind of circuit, okay, we have this circuit over here, and we've talked about this circuit before. Okay, if you don't remember, in a previous slide, it looks like this. Remember, I told you R, we meet from the source, we meet R and then we meet C. So R is going to be at the top and C is going to be bottom. If you meet capacitance first from the source and then you have R over here, then it will be flipped. So in another scenario, this would look like, I believe this is how it looks like last time. Okay, so this guy, in this circuit, you are meeting C and then your R. So this equation would be inverse tangent, sorry about this, it's all over the place, XC over R. But in this case, this is how it looks like. Oh, sorry, we are meeting R and then C. We are meeting R and then C. Okay, yeah. So R over C. Okay, so that's just the way that I remember it, the way that I memorize things anyway. So if that helps you, you can use that method as well, or otherwise you can derive it. I would prefer to memorize it. Okay, again, look where the source starts. You are meeting the R and then the C. So therefore your phi will be inverse tangent R over XC. You cannot divide by C. You have to change it to XC. So how do you change it to XC? This is the equation. C is equal to 1 over 2 pi f xc. And then we're just going to flip it because we have the C, we don't have the xc. We have the F. The F will be at the resonant frequency. What is the resonant frequency? Resonant frequency will be Fc. Okay, so this is what you're going to insert. So 2 pi, 1 megahertz, 40 picofarad, and then you will get the XC as 3.978 kilo ohms. You have your R, and then you can just plug it in, and you will get this answer. So this is the phase angle. Now notice that this is phase angle, not phase shift. How would the symbol phase shift look like? It would look like this. This is phase angle. This is phase shift. What is phase shift? It is the difference of two different phase angles. Okay. If they give you C and they ask you about phase angle, you would, and they give you a circuit, obviously. So you will have to use this kind of method. Okay. We have seen this circuit before. So I hope I hope you are not panicking lah, looking at this circuit. Okay. Revise if you need to. Okay, so next question is, if the modulating signal changes, okay, so FM is changing, the varactor capacitance to 55 picofarad, what is the phase shift? Okay, so now we have a new C, which means that our XC is going to change. So C new is 1 over 2 pi F XC, okay, so here I'm supposed to write it new. Tak apalah. So this is XC new, 1 over 2 pi FC new. Okay, I forgot to edit that. This one as well. Oops. Okay. Okay, so this is all new. So 2 pi, 1 over 2 pi 1 megahertz, because we are still at this is still the resonant frequency, and we are changing it to 55 picofarad. So now the XC new is 2.893, and the R is the same because R does not change. Only the varactor is changing the capacitance value. So the phi new, or the phase angle that is new, is R over XC new, and you will get this new value. Okay. So now what is the phase shift? So phase shift is again the difference between two phase angles. So we have a previous phase angle from our 40 picofarad, and then we have a new phase angle from our 55 picofarad. So you just minus the two. This is the old one. Okay. So 48.74 radians minus 39.68 radians, you will get the answer. Okay, any questions? Was that clear or was that confusing? Is everyone okay? Okay, no questions, huh? Right. So if you have any questions, you can just unmute yourself. Okay, moving on. C. If the modulating signal frequency is 400 hertz, what is the approximate frequency deviation? So you have FM is given. It's asking for FD. So obviously, if you have FM, you have FD. The only thing that we can relate these two together is this equation. Okay. So we are going to use that equation. FD equals to phase shift times with FM. So without the two different phase angles, you would not have the phase shift. So if you did not solve for B, you would not be able to do for C. So this kind of question is a little bit tricky if you decide to skip a problem. Okay. So for using the value that we got from B question, which is 9.06 radians, this is the phase shift. So it's asking us what is FD. So we are plugging in our phase shift. We have our FM, which is 400. So therefore, we will get the frequency deviation as 3.624 kilohertz. So what is the center frequency of this circuit? It is still the carrier frequency. If they ask you what is the center frequency, it's always going to be the carrier frequency. So if they ask you that, we can have another question here. What would be the maximum? What is the range of frequency for this circuit? Oh my God. Okay, maybe I should type this. Okay. Okay. Okay, let's do this. What is the range? This is another question that is possible of frequency for this circuit. So how would you answer this? So the answer would be FC plus minus FD. Plus minus FD. Where's the C break? Okay. So that would give us 1 megahertz plus minus 3.624. Kind of small, but yeah, that's what the question wants. Okay, is that okay?
Okay.
Okay, so this question has a loophole. So it's asking what is the range of frequency for this circuit. Well, when we only discussed about 55 picofarad and 40 picofarad, which is not really ideal. Okay, let me redraw the diagram just now. So this is at FC, we would get 40 picofarad, and at some other frequency you would get 55 tadi, 55 would be here. At a smaller frequency you would get 55 picofarad, but we don't know what the value here is. So this question, I'm answering this question with the assumption that this is symmetrical. The change is symmetrical. So it goes up by 15 picofarad, it goes down by 15 picofarad. Therefore, the deviation is also symmetrical. That was the assumption that I had to make to answer this question. But if this question was really like bulletproof or like, fault proof, I would provide another value over here, which shows the range of the capacitance. Okay. I hope I didn't confuse you, but I'm just saying for people that are thinking extra, but that this question is not fault proof, I am assuming that the behavior is symmetrical. Okay. Okay. Moving on. So we are going to talk again about quadrature detector. Okay, I'm going to give everyone 5 minutes. Take a drink, stretch yourself. I want everyone to understand quadrature detector very carefully. Okay. So let's come back at 11:30. If you have not signed in your attendance, please do so. Alamak. Tertutup. Am I still there? Okay. Okay. Hmm. Lambatnya 11:30. Menyesal pula. 11:30. Okay, let's continue. So now that we have done some exercises to get our brains working and you already got a break, so let's try to focus for the next part. Okay, this is going to be on quadrature detector. Okay, first off, the word detector. What does it mean? Detector means demodulation or detecting the FM signal from the modulated signal, right? So remember that we have our transmission TX, and then we are receiving RX, and what we are transmitting is our modulated signal, which was either AM signal or FM signal. How did we get AM and FM? It's from FC with not plus lah, with FM, right? You have to have the carrier, you have to have the modulating signal to either produce AM or FM. And then you would transmit AM and FM, and the receiver would demodulate the AM or the FM signal to produce FM back again. Why? Because FM is where the signal is, the signal that we want. FC is just a carrier. It helps to transmit the signal that we want to send. Okay. So detector means to demodulate or to like detect the FM, the message signal. Okay. So hope everyone understands this part at least. Okay, so for the quadrature detector, you can see that we have an FM input, and then we have a phase detector, and then this guy is pulse averaging low pass filter. So let's just call it LPF, low pass filter, and we can just make it a box. You don't have to think too complicated about it. Yes, it's a resistor, but just assume that this guy is a low pass filter, and then you would get FM over here. This guy is a phase detector, and typically you would have a balance, what do you call this? Balance modulator, or sometimes it is called phase detector. So the phase detector symbol can be a box, or it can be also like this, and they would say phase detector. Okay, so I'm gonna undo this. Okay, so here you can see that the phase detector requires, or the balance modulator requires two signals. So here, this is the first signal A, and then the second signal B. Okay, so we are supplying FM input. The FM input is split into two signals, A and B. Split into two signals. The first signal is applied directly, meaning to say there's no phase shift applied. Okay, there's no phase shift applied. I'm using the FM input or the FM wave as it is, and I'm going to call this A. And then I am going to supply the other signal and pass it through a tuned circuit. This is called a tuned circuit. We talked about tuned circuit before. It was to produce a certain frequency. Remember? We talked about crystal oscillators, we talked about tuned circuit, and we decided that tuned circuit is not the best way to produce a certain frequency because it's not stable, and we went for a crystal oscillator. Remember? I hope you remember. Okay, anyway, back to the story. So this signal, the second signal passes through a tuned circuit. It interacts with this tuned circuit, or let's not use interact. It moves in the tuned circuit, and what happens is that it's going to produce the FM wave signal plus with 90 degrees leading, or it is phase shifted by 90 degrees. Okay, it is the same input, but now it's called FM wave output, whereby it is the same FM wave phase shifted by 90 degrees. Phase shifted by 90 degrees. So if we have this kind of signal, 90 degrees is quarter, right? Quarter of a signal. So leading. Leading is, it starts earlier. So it's going to be, this is going to be hard. Starts earlier. So this is our FM wave, and this is the leading FM wave. So it starts earlier by a quarter. I hope I drew it correctly. So it starts earlier by a quarter. It's the same wave, just starting earlier. Okay. Okay, now why do we want to have this kind of situation? Okay, after it has produced these two signals, one is that applied directly, okay, applied directly. The other is fed through a small capacitor into a parallel tune circuit, okay, this guy. The resonant frequency of the tune circuit is almost equal to the carrier of the incoming FM wave, okay. And then due to its capacitive nature, the current through the network, okay, the current through the network leads the input voltage by 90 degrees. This produces an output voltage that leads the FM wave by 90 degrees. Okay, exactly what I mentioned to you. It's the same guy, except that it's starting earlier. So when the FM wave deviates from FC, meaning to say the frequency is higher than FC or lower than FC, therefore the phase detector does not like this and it will detect the difference. Okay. When the FM wave deviates from FC, the frequency deviates above or below FC, resulting in increasing or decreasing phase shift between wave input and FM wave output. Okay, so let's see how that looks like. So I'm going to reiterate myself here. So what happens here is we have an FM wave. This is our wave. We split into two. One is applied directly without any changes. So this is why it's called 0 degrees, because there's no phase shift. And then the other guy, the other signal is passed through this tune circuit. And because of this nature of the tune circuit, it's going to produce a signal that leads the FM wave by 90 degrees. And then these two signals are fed into our phase detector. And this guy produces we are going to multiply these two signals together, and the difference is going to tell us how much difference between the two are. And then it's going to pass through the low pass filter, and hopefully we will get FM or something. Okay. So now A is the input frequency signal, B is the input frequency signal that is phase shifted. B changes from 90 degrees according to the modulation. So when frequency modulation occurs, the carrier frequency deviates above and below. Okay, we already discussed this. So this is when there's no modulation. When there's no modulation, this guy is at 90 degrees. The difference between the two is 90 degrees. Okay, remember, we have our guy, phase detector guy, and then we have our A and we have our B. B is basically A plus 90 degrees. So comparing these two, okay, this is A and this is B. B is starting earlier because it's leading. Okay, so when they have a 90 degrees, exactly 90 degrees phase difference, therefore you would have this kind of pulse, and the detector will detect medium average DC. Okay, bear with me here. Medium average DC is detected at the phase detector. Okay, so when there is no modulation, you would get a medium average DC. So when there is modulation, the FM signal decreases. Okay, it decreases from, so this is our FC, it is below FC. So it is going to start more earlier. It is going to start earlier than 90 degrees tadi itu. It's going to start earlier. This guy is here, right? So it's starting way earlier. Okay, so now the FM is greater than 90 degrees. So when that happens, the overlap of the positive side, the overlap of the binary one is going to be smaller. So the LPF will produce a low average DC. Okay. So let's go back here. It detects the difference between the two pulses, right? Detects, okay, whatever that is. Okay, it detects. And then we have some pulse here. This is what the function of LPF is. It's going to detect what is the voltage. That is the function of the LPF, of this pulse. Okay, so that's the function of LPF. LPF is like a friend that tells you you are good to go. Okay, so that was if the frequency decreases. If the frequency increases from FC, therefore it will start a little bit late. So if it starts a little bit late, therefore the phase difference is going to be less than 90 degrees. Okay, and your pulse detected will be high DC. Okay, the LPF will produce a high voltage. Now, why is this important? Because these voltages will dictate how your VCO operates later for PLL. Okay, so I'm going to say that again. So why is the voltage detection here important? Because the voltage tunes our VCO later. So this is very important for us to understand how the phase detector works. So again, we have three scenarios. This is when there's no signal, meaning to say, this is when the FM is equal to FC. Therefore, the difference between the A and B is exactly 90 degrees because that's the default. And if the frequency is smaller, then the FM difference is greater than 90 degrees. If the frequency is higher, the phase difference is going to be less than 90 degrees. It's like opposite. This guy is going to produce high average DC. This guy is going to produce low average DC. So it's kind of like opposites. Is it opposite this one? This is decrease, low, increase, high. The opposite is this scenario. Okay, so I'll leave it to you on how you want to memorize this. But I want you to understand that the phase detector ultimately compares the two, produces a phase difference, and then from the phase difference, the LPF tells you the voltage. Okay, so this is the summary. So the two input signals are exactly 90 degrees out of phase when there's no modulation, only carrier frequency, FM is equal to FC. So the output pulse is medium DC, and then input frequency is lower, then you would get a greater phase shift, you would produce low DC, and then input frequency higher than carrier, phase shift is less than 90 degrees, and you would get high DC. So is there a way? Okay, so if I were to draw this, do I have, okay, I have a drawing. So if we want to make sense of things, because obviously we don't want to memorize a table, so I have a diagram here that I got from a website. It's from this website, by the way. It's a really good website. So here, assuming that our FC is over here. Is that the right way to do it? Okay, let's just try to say that this is our FC. Okay, if the frequency increases, then you would get a, let's say it's here, you would get a high DC, high amplitude. Okay, if the frequency decreases, then you would get a low amplitude. So I believe the website or the guy that running the website simulated the equation. I know you don't want to go through equations, so just look at the diagram and make sense of it. Okay, so now that we have recapped on what quadrature detector is, we're going to use it for our PLL detector, so phase locked loop. Okay, so any questions before I start on PLL? Is everyone okay? Or just dying inside? Don't die yet. You can die after one, not die literally. No questions? Hello, no questions?
No question.
Okay. 81. Okay, not too bad. Okay, so let's continue with PLL, phase locked loop. The word phase, the word lock, and the word loop. Okay, so here we are comparing phase. We are using a phase detector. That's why it's called phase. Then we have a locked. What does it mean by lock? Lock means that you are trying to match the frequency. When you match the frequency, they are called locked. And then we have loop. Why? Because we have a feedback mechanism. So this is the loop. phase lock loop. Okay, so if you forget what phase lock loop is, it uses phase detector, it frequency matches, and it has a feedback. So here, let's take a look at the diagram. PLL is a type of FMD modulator with feedback. The feedback aims to synchronize the output frequency with input frequency and to make the phase shift between the two signals constant or equal to 0. So this is the diagram. We have our FM input. So it is fed into a phase detector, and we know that the phase detector is a type of modulator. Even though the name is detector, remember that our modulators are actually dual alarm. What do you call dual alarm? Our modulators can function as modulator and demodulators. So this is why we have the same symbol used for detector. Okay, so remember, for a modulator or detector, we need to have two inputs again. So this is our FM input, and we have to have a feedback. And then whatever the output here is, it is going to be passed through the low pass filter, and you will get a voltage signal. The voltage is going to control the VCO. So remember that we compared FM wave A and FM wave B, and from there we detected low, medium, high voltage. So that is the voltage used to control the VCO. When we control the VCO through the voltage, we are going to produce frequency over here. So it's kind of like tuning. You tune higher DC, you will get maybe higher frequency, depending on how you set up the VCO. Okay, so the voltage controls the VCO. The VCO produces a frequency supplied into the phase detector. The phase detector checks, is this frequency VCO the same as FM input? If it's not, then it will produce some signal, and then this guy will continue tuning the VCO until they get the right frequency. This happens on and on until you get the locked phase. Okay. So here we have recovered modulating signal. So apart from producing voltage, you would also have FM. But the FM, you would have to have some kind of structure to produce the FM. We'll talk more about that later. But here it is important to know that here the voltage is supplied. Okay, how it translates into FM, we'll talk more about that. Okay, so PLL has three basic elements: phase detector, LPF, VCO. LPF is low pass filter. Phase detector compares two input signals, FM input and VCO output. VCO output over here, and generates signal based on the phase difference. And then the signal is then passed through the low pass filter to produce VCO's control voltage. Okay, so this is our control voltage. VCO frequency is varied by the DC output voltage from the LPF. Okay. Okay, this is the same thing. Okay, so let's talk about these three scenarios. If there is no input signal, there's no input signal. This guy, 0, no input signal. Therefore, the phase detector outputs 0, the LPF outputs 0. Okay, I think it would be better if I have the diagram here. Yeah, Please give me a minute. Okay. Okay, tak apa. Okay, let's put that. Okay, so phase detector outputs 0. If there is no input signal, the phase detector outputs 0. Okay, and then the VCO operates at free running frequency. What is free running frequency? Free running frequency is the default frequency of the VCO. This is the natural frequency or the resonant frequency of the VCO default. And then if the input signal is close but not equal to the VCO free running frequency, meaning to say the VCO output is not the same as FM input, Therefore, the phase detector produces output voltage proportional to the phase difference. Okay, refer to quadrature detector operation. Okay, so no input, DC voltage is 0. When phase difference equals to 90 degrees, DC voltage is also 0. When phase difference is greater than 90, remember FM phase difference greater than 90 degrees, we got DC voltage low. And then when FM is smaller than 90 degrees, the DC voltage was high. So this is exactly the same as quadrature detector. We are using it here. And then based on the voltage, you would tune the VCO. At some point, the error voltage causes the VCO frequency to equal the input frequency. Therefore, the PLL is set to be in locked condition. Although the input and VCO frequencies are equal, there is a phase difference between them, usually exactly 90 degrees. Or this guy. Okay, when DC voltage is 0, the VCO no longer changes frequency. It remains locked. Okay, so trying to relate back to the quadrature detector. Let's delete that. So previously we showed that at the frequency carrier, we have amplitude was 1. Okay, this was 1 previously. And then I told you if the frequency increases, you would get a high voltage. If the frequency decreases, you would get a low voltage, right? But for the VCO, the amplitude here should not be used, but instead it should be, the reference should be starting at 0, and this would be positive value and this would be negative value, because this is how the VCO is tuned. The VCO is tuned 0 to positive voltage, 0 to negative voltage. I hope I have a diagram for this. I forgot if I have it or not. So basically, if the phase difference is equal to 90 degrees, the DC voltage is 0. Okay, so the frequency is maintained at the natural frequency of the VCO. If the voltage is higher, then you would tune it to become higher frequency. If the voltage is lower, you would tune the VCO to produce a lower frequency. I do have a diagram on that. We will talk more on that later. Okay, so how does forcing the VCO to follow the input FM wave perform demodulation? So ultimately, the aim of this diagram or the aim of this circuit is to produce FM, right? So how does forcing VCO, this guy, to follow this guy, to follow the FM input, produces FM or demodulates the signal? So remember what a VCO does. It produces frequency based on the voltage supplied. If the VCO frequency is not equal to the FM input frequency, the phase detector will detect a difference in frequency and produce a phase difference. The phase difference will keep increasing or decreasing. Okay, the frequencies are different, therefore you would get a phase difference. Okay, and based on the phase difference, you would produce a voltage. The voltage adjusts the signal FVCO here until FVCO is equal to FM input. Okay, so if the frequency matches, the frequency is locked, and therefore you can find out what the FM input is, or the FM in the FM input is. Message, I'm talking about this FM, not this FM. That is confusing. So that is how we are going to get FM. If we cannot detect what kind of frequency this is, obviously you're not going to get the actual message, right? So that is why we need to find out what is the frequency. So the phase difference becomes constant when it is locked. Okay, what happens when it is locked? The phase difference becomes constant, or it becomes the 0 DC voltage, 90 degrees. If the input is a cosine, because it has a 90 degrees phase shift, this guy will be a sine or vice versa. If this is a sine, therefore the VCO frequency will be a cosine. The LPF output becomes a constant voltage. The VCO runs at the required frequency, and the PLL stays locked as long as the FM input doesn't change abruptly. Okay, and the VCO can adjust within its locked range. Okay, so these are the terms that we talked about last time. I'm going to go over it again. So free running is VCO frequency when the voltage is 0, when DC is 0 volts. And then we have capture range, the range of input frequencies around VCO frequency onto which the loop can lock when starting from unlock. So here is the capture range, okay? And then we have lock range, range of input frequencies over which the loop remain in lock condition. So assuming the PLL is already locked, the PLL stays locked as long as the FM input does not change abruptly. What does abruptly mean here? So let's say your FM signal, your FM, this FM signal is over here, okay? And then it moves here, and then because, you know, it is dependent on message signal, it moves here, it moves here. Sometimes there is noise, or the message signal is distorted, or the message signal changes very abruptly, and it goes from here to here, outside of the lock range. Then your PLL is no longer synced or no longer locked, and it has to start over the process again. So this is what it means by abruptly. So it is moving not slowly, but like jumping outside of the range. So this is what it means by changing abruptly from the lock range. Therefore, the PLL goes back to unlock. But if you want to start to lock the PLL, the frequency must be in this range, which is around the VCO free running frequency. If it is too far from the VCO free running frequency, then the VCO is not going to be able to detect it. Okay, so this is like the range that the VCO is willing to operate before it becomes locked. After it is locked, it can move from here to here as long as the change is not abrupt. Okay, all right, so I'm gonna let everyone take a 7-minute break. That was a lot. So let's come back at 12:05. If you have any questions, you can ask me.
Doktor,
Yeah.
dia lock ni macam dia adjust VCO tu dengan frekuensi tu sampai satu situation yang dia akan lock. Macam tu kan?
Yes, it is going to frequency match.
Dia
VCO
akan,
frequency, yes.
bila dah match, dia lock macam tu. Lepas tu dia jadi
When it
constant.
is matched, they will follow the FM wave. So you are able to demodulate the frequency. You are able to demodulate the FM signal. Faham tak? Okay. So before it is locked, it doesn't know what the FM signal is. Okay. So your FM signal is like this and then like this. But the PLL doesn't know this until it matches the frequency of this guy at one point, maybe here. And now it is locked. Now it can follow whatever the FM signal is doing. That is why we have a range, because it's following the FM signal changes. But before it starts locked, it cannot follow the changes, and therefore it's like, nah, nothing happens, did not detecting anything. It's just keep on changing. Maybe this guy is compressed, right? Maybe this guy is stretched, because it does not know what the frequency is yet. So at this point, it's not able to demodulate effectively. Tak boleh. But when it is locked, it can follow the FM signal. If this guy is compressed, it can follow to be compressed. It can go to higher frequency. If this guy is stretched, it can follow to be stretched. Goes to lower frequency. As long as it does not change abruptly, you need to say tiba-tiba jadi macam ni, then your PLL is gone. So it has to start over again.
Faham?
So before this lock happens, they will try to troubleshoot until the same frequency is achieved. So that is what the PLL does.
Dia macam ikut orang punya pace time running lah.
Betul. Yep. You can use that analogy. That is correct. So yeah. So your pace is maybe 6, my pace is 8. I'm trying to catch up to you. Once I catch up to you, my pace is going to be 6, and then if you change to 7, I can change to 7. If you change to 8, I can change to 8. But before I catch up to you, we're not going to be in sync. I'm not going to know what your pace is, right? After I see you, then I know what your pace is.
Hmm.
That's a good analogy, actually.
Okay.
Okay. So please take your break. We're going to continue later at 12:05. Okay, sorry, I'm late. Toilet jap. Okay, so let's continue. We talked about the PLL detector, the terms free running. We talked about capture range and lock range. So that was a really interesting analogy. I'm going to repeat the analogy again. So, not sure if everyone is familiar with how pace for running works. So assume that this is me, this is A lah, okay, not me. This is runner A, and then we have a runner B who is way far at the front. So runner A has a pace of maybe 10. Then 10, let's just say 10. Okay, so this is the speed. And then this guy's speed is going to be much faster, which is 6. So I don't know what this person B pace is. I don't know. I have no clue at all. So I'm just going to like go faster. I cannot go slower, right? Because I know that the guy is at the front, unless the guy is at the back. So assuming that the guy is at the front, the person B is at the front. Therefore, my frequency or my pace has to be faster, right? So my pace has to be faster. Therefore, I'm trying to go fast. So I'm going to go for a 5. And then I tune. I change my pace until up to a point. I catch up to this guy. And I see this guy has a pace of 6. I'm going to change it again. So I'm going to change my pace to 6. Now that I know what the pace is, I tuned it, and then I found the guy. I see that the pace is 6. I'm changing the pace to 6. So now I'm running side by side. So now I see what this guy is doing. So even if the person B becomes tired and changes the pace to 7, I can follow because I can see. And then the guy said, okay, I'm going to go slower. So pace 8. I can follow to pace 8. And then the guy said, okay, now I'm recharged. I can go to a faster pace. So pace 5. I can follow that pace 5. Unless this guy is crazy and goes to like a pace 1, which is, not normal for a human. This is very abrupt, right? This is like 5 to 1. This is very abrupt. So obviously, I don't have the capacity to follow this guy because this is too crazy. This is too much of a jump. So I will not be able to follow this until this guy, goes back to a range that I can actually follow. So this is the range that I can catch up to this guy. This is the range that I can follow when I have catch up with the guy. This is the range that I am not able to follow because that guy is crazy. Okay, so that is an analogy if that works for you. Okay. So moving on to advantages, you can read this. We have already talked about it in the previous class. Okay, so let's go over this example number 1. The FM input to a PLL demodulator. Okay, the FM input. Let's draw it. So FM input, this is our FM input, our phase detector, and this is going to be our FVCO. Okay, FVCO comes from VCO, obviously. I don't know. This tablet is not doing its job for me. And then we have LPF. Okay, LPF is connected here. And then we have our recovered signal. Okay, I tried. Let me try again. FM input. Okay. So the FM input to a PLL demodulator, okay, has an unmodulated frequency center frequency of 10.7 megahertz. To what frequency must the VCO be set? The answer is the same as this. The answer is the same because you're trying to match this, right? Therefore, the carrier for the VCO or the FN, the natural frequency of the VCO should also be the same as your carrier FM input. Okay, so the answer is 10.7 megahertz. This is our reference. So obviously we want to follow the reference. From which component in the PLL detector is the recovered modulating signal taken? So the answer is LPF. Okay. Okay, moving on to the next subtopic, PLL to generate FSK, frequency shift keying. Okay, so let's take a look at this diagram first. Okay, let's make sense of this diagram. So here we have a crystal oscillator reference. Okay, X is crystal, TAL, crystal. Okay, crystal oscillator reference. What does a crystal oscillator do? It produces a stable frequency. In this scenario, it produces 1 megahertz. This crystal oscillator frequency is fed into the phase detector, and then it passes through a low pass filter, LPF, and then the low pass filter produces a voltage that controls the VCO. The VCO produces a frequency, and the frequency goes through a frequency divider. The frequency divider is set to have a value of n. Okay, the value of the division is n, and this guy is controlled digitally. Okay, this is what it means, input from MCU. Just ignore it. It's just controlled digitally. Okay, and then after it has been divided, it should match the frequency reference over here, or the crystal oscillator reference. So the difference between the previous diagram with this, the difference between this guy and the previous diagram is that we have a frequency divider. Okay, we have a frequency divider. And obviously this is our reference. This guy does not change. It's not an FM signal. It's a constant signal. Constant, because crystal oscillator can only be tuned using a circuit. It produces a fixed frequency. These two are the different blocks compared to the PLL detector earlier. Okay, so the feedback comes from the VCO output. So this guy is now going to produce our feedback. The feedback is fed into the frequency divider. Okay, that is applied to the digital frequency divider. This divider reduces the VCO output frequency by a factor of n. Remember, for a PLL to be in stable locked state, both frequency signals to the phase detector must be the same. So therefore, the input for this guy, the phase detector, should be the same. F1 and F2 should be the same. Okay. So this means, from this block diagram, this means that this will produce a phase difference, and from the phase difference is going to produce a voltage after the low pass filter. The voltage will control the VCO. The VCO will produce a frequency. The frequency is some value, and that frequency will be fed into the frequency divider. That frequency is divided by n, and the output should be the same as the crystal oscillator. So VCO frequency divided by n should be equal to crystal oscillator reference frequency for PLL to be stable and locked. To be stable. Okay, to be stable. So n can be changed digitally with 1 megahertz reference crystal oscillator. If n is set to 10, we can generate a 10 megahertz output. So how does that work? So n is equal to 10. Okay, this is our value for n. So this is 1. So 1 megahertz, and this guy also needs to be 1 megahertz. So 1, if we are going this way, we need to times 10. And we know that 1 megahertz times 10 is going to produce 1 megahertz over here. Okay, I know it's a little bit confusing, but I'm just going like backwards. Okay, let me reiterate this again. Okay. What is the function of PLL in generating frequency? Okay, why can't we just use a crystal oscillator to produce a certain frequency? Because crystal oscillator cannot be tuned. Again, crystal oscillator cannot be tuned. It is a fixed frequency. So now I have a fixed frequency crystal oscillator. How do I tune it to be another frequency? Through PLL. So how do I tune it? Using a PLL detector plus the frequency divider. Okay, so how do I change the frequency? The way that I change the frequency is that first I need to make sure the input that goes to the phase detector is the same. Meaning to say whatever the output of the frequency divider should be equal to the frequency oscillator. So if this guy is 1 megahertz, I need to make sure the output is 1 megahertz as well. So if this guy is 1 megahertz and my n is a certain number, in this case my n is 10, going backwards 1 megahertz times with 10 will give me 10 megahertz. Okay, so this is how I can know what my output at the VCO is. If I change my n, the output will also change. So if n is changed to 5, what would the VCO output be?
5
Then you
megahertz.
apa?
5 megahertz kan?
5, yes. It's going to be 5 megahertz. So that is how you tune the frequency using the crystal oscillator. Why is it important to use the crystal oscillator? Because it is very stable compared to a tuned circuit. That is why people keep using it. Okay, so now that we talked about this flow going backwards, let's go through this flow. Let's try to make sense of the block diagram again in the actual flow. So I am supplying 1 megahertz here, 1 megahertz here. If it is the same, it's going to be 90 degrees. 90 degrees, 90 degrees phase shift. And when it is 90 degrees, it's going to produce 0 volts. And if it is 0 volts, it's going to tune at the natural frequency of the VCO, whatever that I tune it to be lah. And the natural frequency in this case is going to be 10. Okay. And if I change this, I can change the entire thing. I mean, this guy is going to control everything lah. So basically, you need to understand how the N works to change the frequency. It's just this equation. Okay, so I have a question. An FSK system being designed assigns binary 0 to 5 megahertz. Okay, this is binary 1, this is binary 0. This is going to be 5 megahertz. 0, 5 megahertz. And binary 0 is 5. Ya Allah. Okay, this is 5. And binary 1 is 5.5. So it's going to be faster than slow. Okay, so this is what it wants to do. A PLL modulator uses a 100 kilohertz reference oscillator. So this guy is 100 kilohertz. What are the divide factors N needed to produce the desired outputs? So here we have VCO frequency times with N, 8 times VCO frequency, divide by N will give me the reference. Okay, my VCO frequency needs to be 5.5 megahertz and 5 megahertz to produce this guy. Okay, my VCO frequency needs to produce 5.5 and 5 megahertz to produce this scenario. Okay, what are the N values that I should control this to get this 5.5 and 5? So my reference is what? 100 kilohertz or 0.1. Okay, so what is N? So N is, I don't know, need to use my calculator. 5 divided by 0.1, is it 50? Macam tak boleh function pula otak saya. Yeah, 50. So N should be 50 and 5.5 divided by, so N should be 50 and 55. So my computer should set this N value of 50 and 55 depending on this binary input. Any questions about this? Yeah? No questions? I hope I'm still recording. My recording. Am I recording? I did not record. Kenapa? Oh, I am. Okay, so wait. Phew. Okay, a little bit more. Bear with me. We have another 6 slides to go. Sikit lagi. Okay, so where do these n values come from? It could be the output of a microcontroller program to send the n values at the desired rate, okay? Or it could be some special digital circuit using FPGA, so you can control it. The speed of sending the n value must be great enough to ensure the desired FSK bitrate is achieved. Okay, so your FPGA needs to like really be fast enough to follow the FSK bitrate. Kind of cool if we can actually do it. Okay, so moving on, let's dive deeper into PLL VCO operation. Remember that I told you that the LPF produces a certain voltage, and from the voltage, we control the VCO frequency, right? Okay, this guy VCO. This one is voltage. Okay, the LPF produces some voltage, the VCO produces some frequency based on the voltage. And this, whoa. Did you guys hear that? Someone just sneezed and I can hear it from here. I think it's outside. That was epic. Okay, so frequency VCO and this is FM input, right? So this is the DC bias voltage produced by the LPF. So if it is 0, then it would operate, the VCO would operate at its natural frequency N, the default frequency. If the DC voltage is higher than 0, then the VCO is tuned to be a lower frequency than Fn. If the DC bias voltage is negative, then the frequency would be increased compared to Fn. This is how it functions. So the LPF dictates what frequency the VCO produces, either higher than Fn, lower than Fn, or equal to Fn. So the transfer function or conversion gain K of the VCO can be expressed as delta F, change in frequency, over the change in voltage. K is basically the sensitivity of the VCO. So how sensitive is it to voltage? How sensitive is it to voltage? So do you need a higher voltage to produce a small frequency, or do you need like a small voltage to produce a change in frequency? So that determines the sensitivity. So K is the amount of deviation of frequency per unit change in delta V. So do we have an example of that? Okay, this one. So an example of this is the output frequency of VCO. Okay, so our frequency changes from 100. So F1 is 100 kilohertz. F2 is 150 kilohertz. When a change of 0.5 volt occurs. Okay, our delta F is 150 minus 100 kilohertz. It's going to be 50 kilohertz. This is our delta F. Calculate the conversion gain K for the VCO. So K is delta F over delta V. Tells us the sensitivity of the VCO. 50 kilohertz divided by 0.5 volts. Whatever this value is, or you can just leave it like that. That would be the answer as well. Kalau kita kira, if we calculate this, 50 divided by 0.5. So is it? Oh, salah. 100. That would be 100 kilohertz per volt. I skipped this one. Okay. Jap. This one I'm gonna cover tomorrow. This one. Okay, let's go over this one. Last slide. Okay, so final slide, bear with me just a little bit more. So PLL VCO operation, we talked about this guy. We know that at 0 DC bias voltage, the VCO operates at its natural or default frequency. If we change the DC bias, the frequency also changes. Positive bias give us negative or smaller frequency. Negative bias give us higher frequency. So the output frequency of the VCO decreases below Fn when the DC voltage becomes increasingly positive, and vice versa. So the VCO's frequency of operation can be stated as FVCO Fn, which is the natural frequency or the default, plus minus delta F, assuming symmetrical frequency deviation. Symmetrical, meaning to say, if I change this by 1, maybe the drop is 10 kilohertz. If I change this by -1, the increase is 10 kilohertz. This is what it means by symmetrical. The drop in voltage or the increase in voltage produces similar value of drop or increase in frequency as well. That is symmetrical. What is a scenario that is not symmetrical? If I increase the voltage by 1, the drop is maybe 9 kilohertz. But if I drop the voltage by -1 or drop the voltage by 1, the increase is 11. So obviously the voltage increase and decrease is not the same as the voltage increase, and it's not the same as frequency increase and decrease. So that is not symmetrical. Symmetrical means the rate is the same, the change is the same. Okay, so this equation is assuming symmetrical frequency deviation, which is not always the case, but we can assume, ideally. Okay, so that is today's class. Do you have any questions for me? Stop sharing. No questions? Everyone is okay? Or was that what? Too confusing?
Dia macam barely understand je lah. Tak adalah faham sangat.
Okay, so hopefully tomorrow we can reinforce our knowledge. Tomorrow we'll still be on PLL. I can say that PLL is a very famous question to come out. So please make sure if you don't understand, you should ask me in class. Okay. All right. So thank you, everyone. Have a great rest of the day. I'll see you tomorrow. Bye-bye. Don't forget your attendance.
Thank you, Doctor.
Thank you, Doctor.
Okay.
Thank
Bye-bye.
you, Doctor. Thank you, Doctor.
Thank you, Doctor.
Doctor.
Bye-bye.